Greetings and welcome to Precalculus, Graphs and Functions. In this lesson, we're going to be concentrating on combining functions and composite functions. All right, let's start with combining functions. Functions can be added, subtracted, multiplied, and divided. So if you have two functions, they can be added together, or you can subtract them, multiply them, divide them. And you're really going to focus on like terms when you do this. Let's have an example of f of x equals x squared minus 2x plus 4 and g of x equals x plus 2. And let's go through and we'll add them, subtract them, multiply them, divide them. So let's first add them. So f of x plus g of x would equal x squared minus 2x plus 4 plus x plus 2. Now we're going to combine like terms. So the only like terms I have minus 2x plus x is minus 1x, and 4 plus 2 is 6. Okay. Now we can write this f of x plus g of x in terms of f plus g. You can also see it as f plus g of x. But the result will be, if you add function f to function g, you'll get x squared minus x minus 6. Now we do have the option of adding, subtracting, multiplying, and dividing functions. So we have the sum, difference, product, and quotient. How we're going to notate this is, for sum, it will be f plus g. For difference, f minus g. For product, fg, and for quotient, f divided by g. Now, when we're doing this, we need to set up some definitions so we understand what we mean by this. The sum f plus g of x, well, you're going to take f of x plus g of x. Order is going to matter for most of these. Of course, not for addition, not for multiplication, but definitely for taking the difference and the quotient. Order matters. Okay, the difference, f minus g of x, that's going to be f of x minus g of x. Always be careful when you're taking the difference that you distribute this negative to everything in g of x. Fg of x is going to be f of x times g of x. And the quotient, f divided by g of x, will be f of x divided by g of x. But you have to make sure that g of x is not 0. We cannot have g of x be 0. So when we're given a value, we got to be very careful when we evaluate it that the denominator is not 0. The domain of each of the results of the function are the x values that are in common with f and g, not just f, not just g, but what they both have in common. All right, let's take a look at some functions here. Let's take a look at f of x is x squared minus 6x plus 8, and our g of x is x minus 2. Let's go ahead and look at a couple of ways of doing this. First of all, f minus g of 4, f divided by g of 3, f plus g of x, x minus g of x, fg of x, and f divided by g of x. We'll look at all 6 of these one at a time. All right, for a, f minus g of 4. There's a couple of ways that we can do this. Number one, we could do the subtraction of the functions and then evaluate it at 4. So one option is, let's go ahead and figure out what f minus g of x is. So f is x squared minus 6x plus 8, and g of x is x minus 2, so we're going to subtract out g of x. It's going to be very important that I distribute this negative not only to the x, but the 2 as well. So I get x squared minus 6x plus 8 minus x plus 2. Combine like terms. And the result is x squared minus 7x plus 10. So this is what f minus g of x is. But now we need to evaluate it at 4. All right, so let's go ahead and plug in 4 wherever we see an x in our result. 4 squared minus 7 times 4 plus 10. 4 squared is 16. 7 times 4 is 28, so we're left with 16 minus 28 plus 10. And we ultimately get negative 2. That's your first option. Figure out what the functions are combined, and then figure out what it is at that value. The second option is, well, I can plug in the 4 immediately. So instead of using the x squared minus 6x plus 8, I'm going to use 4 squared minus 6 times 4 plus 8. And in the x minus 2 for the g function, I'm going to use 4 minus 2. And I'm going to run through doing the math. 4 squared is 16. 6 times 4 is 24. 16 minus 24 plus 8 is going to be, well, 16 minus 24 is negative 8. Negative 8 plus 8 is going to be a 0. And I get 0. 4 minus 2 is 2, minus 2, and I still get negative 2. So whether I figure out what the functions are combined first and then evaluate it, or go ahead and evaluate it while you're putting the functions together, just really remember your order of operation here. Either way will give you the answer. If you are going to do several of these f minus g, I would go ahead and combine the functions first. Otherwise, if you're only going to do it once, well, then you can jump to evaluation as you go. All right, let's look at b. F divided by g of 3. And again, I have two options. One, I can figure out what my functions are combined, or I can just immediately put in the value at 3. So I'm going to go ahead and put in the value at 3. So 3 squared minus 6 times 3 plus 8 all over 3 minus 2. All right, 3 squared is 9. 9 minus 18 is negative 9. Negative 9 minus 8 is negative 1 all over 1, and therefore my solution is 1, negative 1. Now I do need to be careful that whatever value I have in this denominator, it's not 0. If I did get a 0, then the whole entire thing would be undefined. Not just g at that value, but the whole entire f over g of 3. All right, let's look at c. F plus g of x. We don't have an actual value that we're evaluating it. We're just combining f of x and g of x. Okay, so f plus g of x is going to be f of x, x squared minus 6x plus 8, plus g of x, which is x minus 2. Combining like terms, I get x squared minus 5x plus 6. So I get to combine the negative 6x and the plus x, and the plus 8 and the minus 2. And that's it. That is my answer. I can't go any further because they didn't give me a value for x. Let's look at D. F of g of x. Now in option 1, we actually already figured this out, but let's run through it one more time. F of x is x squared minus 6x plus 8. G of x is x minus 2, and we're going to subtract them. Again, be very careful to distribute this negative through. I get x squared minus 6x plus 8 minus x plus 2. Combine like terms, and we get x squared minus 7x plus 10. Again, we can't go any further because they didn't give us a value for x. Let's look at fg of x. This means multiply. So I'm going to take f of x, x squared minus 6x plus 8, and multiply it with x minus 2. Now, just how my brain works, I actually like, because, 2 times 6 is the same thing as 6 times 2, I can order these any way. So I actually like this binomial in front of a trinomial. For me, it's a little bit easier to multiply it that way. So I'm going to go ahead and rewrite it to where the x minus 2 is in front, and then I'm just going to FOIL this through. I'm going to multiply x by each term in the second, and then negative 2 by everything in the second term, second blob, if you want to call it a blob. All right, x times x squared is x cubed. X times negative 6x is negative 6x squared. X times 8 is plus 8x. Negative 2 times x squared is negative 2x squared. Negative 2 times negative 6x is positive 12x. And negative 2 times positive 8 is negative 16. We're going to combine any like terms that we can. X cubed, nothing else to combine. I do have the negative 6x and the negative 2x, making it negative 8x squared. I have an 8x and a 12x for 20x, and 16, I have nothing else to combine. So fg of x will be x cubed minus 8x squared plus 20x minus 16. All right, last one that we're going to do for this example. Let's do f over g of x, or f divided by g of x. All right, f of x is x squared minus 6x plus 8, x minus 2 over x minus 2. Now I'm going to factor this numerator to see if there's anything that I can reduce. I could do long division, but I find that if I can factor it, that's a little bit easier way to work with it. And it turns out that x squared minus 6x plus 8, it factors into x minus 4 times x minus 2. The x minus 2's will cancel out, they'll reduce, and I am left with x minus 4. But I do need to say one thing. X is not allowed to be 2, because if I had a 2 for my x value, I know we're not given one, but if I was given x values, it cannot be 2 because 2 minus 2 gives me a 0 down in the denominator. So that's a big no-no. Otherwise, our answer would be x minus 4 as long as x does not equal 2. Now that brings us to a really good point. We need to know what our domain is if our domain has any limitations. Does it have any restrictions on our domain? So let's say we have our f of x is the square root of x plus 2. G of x is the square root of 5 minus x. Now, here's the thing. If I just had f of x, this value inside my radical must be 0 or a positive number. Otherwise, I'm not in the real numbers. For g of x, likewise, this value inside the radical must be 0 or a positive number. Otherwise, I'm not in the real numbers. In other words, it can't be negative. Inside the radical cannot be negative. So we have to keep that in mind. But anytime that I combine these two functions, both of the limitations for f of x and g of x must be upheld. Okay, let's look for the domain for f plus g, f minus g, f times g, and f divided by g. Let's do this one at a time. And in fact, we could actually do 3 of them all at once because f plus g, f minus g, and fg all have the same domain. But let's run through it really quick and see what's going on. I know for f of x, my domain, this x plus 2 must be greater than or equal to 0. So I'm going to solve this. I'm going to subtract 2 from both sides, and the domain of f is x is greater than or equal to negative 2. You've done this before. So finding the domain of one function, you've already done. Let's take a look at the function g of x equals the square root of 5 minus x. The domain here is when 5 minus x is greater than or equal to 0. I'm going to go ahead and solve this for x. First, subtracting 5 from each side, but now I have a negative x, so I have to divide by negative 1. But the rules are, if I divide by negative 1, I have to flip the symbol, the inequality symbol, and I get x is greater than, less than or equal to 5. My domain for f plus g, f minus g, and fg, these two things must be true. Must be true. And therefore, for these guys, f plus g, f minus g, and fg, it's going to be the combine of my two domains, meaning -2 is less than or equal to x is less than or equal to 5, because it has to be greater than -2, but less than 5, including those two. Now the complexity comes when we're talking about the division. Right? So when we are looking at the division of f divided by g, our domains for the individual functions are exactly the same. There's no new work to do. There's only a little issue that we need to consider. Since f of x domain is x is greater than or equal to -2, and g's domain is x is less than or equal to 5, but g is in the denominator, we can't let it be 0. And therefore we can't let x be 5. So it's just one slight little change of the domain. And it's going to be -2 is less than or equal to x less than 5. We're not allowed to include 5 with the division. We're allowed to include the 5 for the other combinations of combining of functions. Let's step away from combining functions with addition, subtraction, multiplication, and division and move on to composition of functions. That means that a function is going to be inside a function, and order is going to matter a lot here. So if we have our functions f and g, the composition of function f with the function g is going to be written with this little circle in between them. I know it looks like fog, but this is just a little circle. So it's going to be f of g of x, or you can say f composed with g of x. I just say f of g of x. It's just a lot faster to say. What this means is for every x value in f, you're going to put the whole entire function g of x inside of that x. You'll see when we start looking at some examples what I mean by placing g of x inside wherever you see an x in f. And this order really does make a difference. Okay, so here we go. Let's just look at a kind of a picture of what we're doing. We get an x value, we put it in g, and we evaluate it. And then whatever we get out of this g of x, we then place it into f, and we get an outcome of f of g of x. So you have this extra step. Now we are allowed to go straight from x all the way over to f of g of x as long as you're, well, I want to say mentally making sure that it's the whole entire g of x that you're placing in f. So let's take a look. Let's let f of x be x cubed, and let's let g of x be x plus 1. And we're going to figure out a couple of things. First of all, we're going to do f of g of 1. Then we're going to do g of f of 1. And then f of f at 1. Yes, you can do a composite function with itself. That's totally permitted. Let's take a first. F of g of 1. Here's what it means. The second value, which is g, my second function, which is g, I'm going to evaluate it using a 1. So I am literally going to put a 1 in here, figure out what it is. Once I figure out what g of 1 is, my result, I'm going to put it into f of x. Here we go. Method 1 is first I would find f of g, and then I would evaluate it using the 1. So this is method 1. All right, wherever I see an x, I'm going to put the whole entire function g of x. So here's my x. I have to place this whole entire x plus 1 inside the x, and I get x plus 1 cubed. Now I would evaluate it with 1. 1 plus 1 is 2. 2 cubed is 8. So f of g of 1 is 8. You can see that's much different than f of 1. F of 1 would be 1 cubed, which is just 1. But this is 8. That's method 1. The second method is to evaluate g of 1, figure out what that is, and then place it into f. So let's look at method 2. Evaluate g of 1 first. So I'm literally just going to take g of x, which is x plus 1, evaluate it at 1, which is 1 plus 1, and 1 plus 1 is 2. Now I'm going to place this 2 inside where f of x is. F of x is x cubed, so I'm going to use this f of 2 is 2 cubed, and therefore I get 8. So it's evaluated at g of 1 first, get your result, and then put your result inside f of x. That's method 2. I actually find that method 2, unless I'm going to do a lot of these f of g's, I think going the direct right and first putting in g and then finding your result and putting in f is pretty straightforward. If I'm going to do a lot of these f of g's, maybe f of g of 1, f of g of 2, f of g of 3, then I would probably go through, I don't want to say the hassle, but I would go through figuring out what f of g of x actually is before I placed any numbers in it if I was going to do more than one. All right, let's do f of g of 1 equals 8. Okay, second one, g of f. And again, I can use either the first method or the second method. I'm going to show you both methods. The first method is, let's go ahead and find g of f of x. So wherever an x is, I'm going to go ahead and let you see everything here. Wherever an x is in f of x, let me see if I can get my language right here. Anywhere you see a x in g, you're going to place the whole entire f of x in there. Now remember, g is x plus 1. F of x is x cubed, so wherever I see the x plus 1, I have to put the whole entire x cubed here. So I get x cubed plus 1. Now I'm going to evaluate it at 1. So wherever I see a 1 here, or wherever I see an x, I'm going to place a 1. So 1 cubed plus 1. 1 cubed is 1. 1 plus 1 is 2. That's the first method. Let's take a look at the second method. The second method is, first you do the end one, f of 1. So we're going to do f of 1. Place a 1 wherever we see the x. 1 cubed is 1. Now the result is, take this result and put it in g of x, and we get 1 plus 1, which is 2. I want to stress this particular one is part of what we were given. This one is a result from doing f of 1. I don't want to say they're two different ones, but they are two different ones. So g of f at 1 is 2. You notice f of g of 1 is 8. G of f of 1 is 2. Order matters. They're generally not going to be the same thing. Now let's do the third one, f of 1. And I'm going to do both methods really quickly. Okay, f of x, wherever I see an x, I'm going to put f of x inside it. So I've got x cubed inside the x cubed. X cubed cubed is x to the 9th. And then I would put in a 1 there, and 1 to the 9th is 1. The second method is do it one step at a time. First do this f of x, and then do the second f of x after you get the result. So f of x is x cubed, place a 1 in there. 1 cubed is 1. From 1, you're going to put it into f of x again, and you get 1 cubed, which is 1. Same answer, two different methods on how you get the answer. You might feel you're very comfortable about putting a function inside a function, so you might do method 1 first. If you're not comfortable with that, then break it down into a couple of steps. Do the second function and then take the result and put it into the first function. The domain of a composite function. Again, we're going to have to make sure that our domain of the composite meets all of the specifications of each function themselves. Okay, so let's take an example. F of x is 2 over x minus 3, and g of x is 5 over x plus 1. If I look at f of x, I am not allowed to have the denominator be 0. So x is not allowed to be 3. And if I look at g of x, the denominator again is not allowed to be 0. So if x is negative 1, this would cause it to be 0. So my f function has the restriction x cannot be 3. G has the function of x cannot be negative 1. Now let's find the domain of this inner function. We looked at it separately, but separately isn't always the case. So let's look at this inner function. We're doing f of g, so the inner function is g. We know that the domain is all values except for negative 1. Not allowed negative 1. We already figured that out just by looking at there, hey, the denominator is not allowed to be 0, so I need to solve for what causes it to be 0, and that's negative 1. Now, we have either in set notation all x's such that x is not equal to 1, or in interval notation negative infinity to 1, not including 1, 1 to positive infinity, again not including 1. The second step is to actually find this domain of g inside f, our actual composite. So placing our g of x wherever we saw an x here, I have to place this whole entire thing right here in the x. And I get 5 over x minus 1 minus, or x plus 1 minus 3. It's this whole entire denominator is not allowed to be 0. So let's bring it off to the side and let's solve for what causes this to be 0. I'm going to add 3 to both sides, and then I'm going to get rid of this x plus 1 down in the denominator by multiplying x plus 1 to both sides. I get 5 equals 3x plus 1. 5 equals 3x plus 3. Again, solving for x, I end up getting x is 2/3, okay? So because originally we have to worry about this denominator being 0, we have a restriction that x cannot be negative 1. And now this whole entire denominator cannot be 0, and we have the restriction of 2/3. So if you're looking at it on a number line, you're not allowed to be negative 1, so that would be an open circle. You're not allowed to be 2/3. That's an open circle. And so we have this block is okay, this block is okay, and this block is okay. So our interval notation is going to be negative infinity to negative 1, unioned with negative 1 to 2/3, unioned with 2/3 to positive infinity. And these are all parentheses, meaning I do not include negative 1 and I do not include 2/3. Now you may have noticed I did talk about this x minus 3 being 0. But in this composite function, that did not matter. It was the whole entire denominator after it was embedded with the g of x, which mattered. So 3 is totally allowable because this is no longer just 3. It is 5 over x plus 1. I hope that makes sense. Let's run through a few more examples of finding the domain of f of g. Let's say our two functions, f of x is 1 over x, and g of x is 3x minus 12. And remember, I'm putting g of x inside f of x. First things first, is there any restriction on g of x? Okay, well, no, because I don't have a square root and I don't have a denominator. So we actually do not have any restriction on the g of x portion of this problem. So my whole entire domain of g of x is from negative infinity to infinity. Now once I actually compose my f of g of x, then let's see if we have anything. So I'm going to place this 3x minus 12 right inside the denominator of f of x. And sure enough, now that I have my x in the denominator, I might have a problem. I don't want my denominator to be 0, so I'm going to solve this side little problem. Add 12 to both sides, and we get 3x should not equal 12. Divide by 3 both sides, and we get x should not be 4. Now, the g portion of it, we are totally allowed everything. But once we get this g inside f, we are no longer allowed 4. And therefore, our domain for the f of g is going to be all x's such that x does not equal 4, or in interval notation, negative infinity to 4 union with 4 to infinity, not including the 4 on both of those. Okay, let's take a look at another one. Let's take a look at f of x is the square root of x minus 2. G of x is the square root of 4 minus x. And again, we want to find the f of g. We're going to place g of x inside f of x and figure out what the domain is. But we have an issue here. First of all, what is the domain of the inner function, which is g of x? I'm not allowed the square root of a negative number. So let's figure out both f of g and g of f, the domain. First of all, if I'm not allowed the square root of 4 minus x to be negative, it has to be greater than or equal to 0. Let's solve this problem, subtracting 4 from both sides, and then dividing by negative 1. Remember, anytime that you divide by a negative 1 with inequality, you need to flip the symbol. So x must be less than or equal to 4 for this to work. Now, let's place g of x inside f of x. And again, this whole entire object inside the big radical must be greater than or equal to 0. So let's solve this. Add 2 to both sides, and I get the square root of 4 minus x is greater than or equal to 2. Let's square both sides. I get 4 minus x is greater than or equal to 4. Solve this for x, and we get x is greater than or equal to 0. Okay? X is greater than or equal to 0. So we have to be less than or equal to 4, but greater than or equal to 0. So we have to be this. When you think about it, I could be less than 4, but I have to be less than 0. So anything above 0 is not in the domain of f of g. So I'm not allowed to go all the way up to 4, even though my g allowed me to go way up to 4. I have to make sure that it's acceptable for both of the functions, or I should say the composed function. So x such that x is less than or equal to 0, or negative infinity to 0, including 0. Now let's take a look at the second version, g of f. First thing first, our inner function is f, so we are going to need to find the domain for our function f of x. So again, I'm not allowed to have anything in the radical be less than 0. So let's figure out where it is greater than or equal to 0. And we find that x must be greater than or equal to 2. It cannot be less than 2. It has to be greater than or equal to 2. Now placing f of x inside g of x, we get the square root of 4 minus the square root of x minus 2. Figuring out where this is greater than 0, because again, inside this whole entire radical needs to be greater than 0, we get 4 minus square root of x minus 2 is greater than or equal to 0. I'm going to subtract 4 from both sides. I'm going to divide by negative 1, flipping the symbol as I do it. I'm going to square both sides so I can get rid of the radical. I get x minus 2 is less than or equal to 16. Add 2 to both sides. X is less than 18. But remember, I already had some restrictions. It was greater than or equal to 2, less than or equal to 18. Putting those two things together, I get my domain of g of x is going to be all x's such that 2 is less than or equal to x is less than or equal to 18. In other words, in interval notation, 2 to 18, including the 2, so it's a bracket, including the 18, so it is a bracket. You have to make sure where does it overlap. You can sketch out the number line if you want. If that helps, it's the overlap. All right. Sometimes we want to decompose a function. So let's say we have some function, it's called h, and it is actually the composition of functions f and g. And I'm given what h is. Now I want to say when you are decomposing functions, there are numerous answers that it could be. Try to go for the most straightforward one. Okay, so h of x equals 1 over the square root of 2x squared plus 1. So here's what I'm going to do. I'm going to allow g of x to be what's inside this radical. Okay, so 2x squared plus 1. I'm selecting it. I'm totally allowing it to be this. Then we have, well, h of x would be its original form, or it could be written as 1 over the square root of g of x. Now when I composed the function f of g, wherever I had an x inside f, that's where I put g of x. So let's let f of x be 1 over the square root of x. As you can see, that's where g of x is. So we can say that h of x is the composed FOG, where f of x is 1 over x squared, and g of x is 2x squared plus 1. Now I chose this. Again, this can be a lot of different things. I could have chosen, well, let's let g be x. And then I could have made f 1 over 2x plus 1. Something like that. Maybe x could be x squared. And then I could have chosen a lot of different versions. This seemed to just scream out at me. Just select this whole entire thing and replace it with x. Right? Again, you had lots of options here. Here's another option. I'll write it down. Let's see. Get my pen out here. Here's another option. So starting back at h, I could have said, well, let's let g of x equal x squared. And then I'm going to say f of x will equal 1 over the square root 2x plus 1. This is another option because you can see if I put this 2x or x squared right there, I get back to h of x, 1 over the square root 2x squared plus 1. There are several answers. This is just one possible solution. Okay, that's one possible solution. Here is another possible solution. I could have decided, okay, well, maybe instead of x squared, I could have said, let's see, 2x. And then therefore f of x would be 1 over x plus 1. So if I chose this to be my functions, wherever I see a 2x, or it would be 2x squared, it would go right here. Right? So there are lots of different versions of what the two functions could be when you're breaking something down. Think about this. When you cut a pie, you can cut the pieces this big, or you can cut it from the top, or you can cut it from the bottom, of the round pie. You can cut it from the north side, the south side, the east side, the west side, and take a sliver out and see what's left over. You could cut half the pie and you'd have two different sides of the pie. But if I wanted you to cut it in two pieces, specifically two pieces, you'd cut it down the middle and you'd have half and half. That still makes the whole pie. You could cut one slice out That's a quarter of a pie, and the rest is 3/4 of the pie. And that's a way of cutting it into two pieces. But when you put it back together, you still get the whole pie. It's the same idea. You have two functions, but when you compose them, you still get back to the original function. How you decompose it, as long as you get back to the original, is up to you. Okay, so up to you in that sense. Lots and lots of different ways to do it. Let's run through really quickly a couple of applications of composite functions. So let's calculate the area of an oil spill, but this is going to be based on time. Let's suppose an oil spill from a tanker is flowing into the ocean. The area of the spill is a perfect circle, but the radius of the circle increases 2 miles per hour. So for every hour, it increases by 2 miles, this radius. Well, that means that we actually have a function inside the function. We have this growth of the radius inside the area of the spill. So let's take a look at how do we get our function within our function, and then we'll calculate, well, what is the area covered by the oil slick in 6 hours? So first of all, area is a function of time. We know the area of a circle is based on the radius. So area of the circle is pi r squared. So this function is actually based on the radius. So function of r, f of r, is pi r squared. I've just replaced the a with function notation and called it f. I could have called it a, doesn't matter, but we'll call it f of r. But it's based on the radius. Now remember, our radius increases 2 miles per hour. So our radius is 2 times the time. So for every hour, it increases 2 miles. So our radius is based 2t, and therefore our growth is based on time, and our time is 2t. Our g of t is 2t. And you can get this by our distance formula. Distance equals rate times time. So that's kind of how we got it. Okay, but now we want to create this function, the area function of time. So wherever I see an r right here, I'm going to go ahead and use g of t. So g of t is going to go inside f of r. And we get f of g of t is f of what? 2t. So wherever I see 2t, wherever I see an r, I'm going to place 2t. So our function, our area, is no longer pi r squared, it's pi 2t squared. Now it's based on time. It's no longer based on radius. It's all about time. Now that we know we have time, let's go ahead and figure out how large it's going to be in 6 hours. So that's going to be f of g of 6. So let's throw a 6 in there since we already know what our function is. Pi times 2 times 6 squared. 2 times 6 is 12. 12 squared is 144. And 144 times 3.145 is going to be about 452 square miles. So after 6 hours, this oil spill will be about 452 square miles. And if you wanted to know what it would be after 3 hours, you can plug in a 3. 3 times 2 is 6. 6 squared is 36. 36 times pi is approximately 100 and something square miles. Yeah. So you can figure out what it would be with just time now. You don't have to worry about, well, what was the radius of the circle? Well, I don't know. I'm not going to go and measure it, but I know how much time elapsed. All right, so that's one application. Let's take a look at another example of applying this composition, but this time a car dealership. So a car dealer offers 8% discount off the manufacturer's suggested retail price, MSRP, of however many dollars any of the new cars on the lot. At the same time, the manufacturer also offers a $4,000 rebate for each purchase of a new car. Now we want to come up with a way of figuring out, okay, well, we know what the rebate will be. So this is going to be after the rebate only. What the discount price would be, this is going to be the price after discount only. And then we're going to figure out rebate composed with our discount and our discount composed with our rebate, and see if these two things are any different. Think about it. Do you believe that the rebate composed with the discount is going to be the same as the discount composed with the rebate? We'll find out. And then we're going to subtract the two, and if this is not 0, then these two are not equal to one another. If they are the same, then it's going to be whatever it is minus whatever it is, and that would be 0. So if these two compositions are exactly the same thing, when we calculate D, it's going to be 0. All right, let's take a look. We know the MSRP is X. We also know we get a $4,000 rebate, meaning whatever the price of the car is, minus $4,000 is going to be our rebate, our price of our car after rebate. So let's say our car was $20,000. $20,000 minus $4,000 is $16,000. That's the price of our car after the rebate only. So price after rebate only. Let's do the second one. Let's figure out what the price of the car would be after a discount only. Okay. All right, our MSRP is still our X value. Our discount is 8% or 0.08. To figure out the discount, I take the price of the car, I should say, the price of the car after the discount will be the price of the car minus the 8% discount, which is 0.08 times the price of the car. In other words, we only have to pay 0.92 of the car price. Think about this. If you have to pay 100% of the car price, if you get an 8% discount, you're really paying 92% of the car price. So 0.92 times X will be our new discounted price. Now let's do both C and D. We'll do our compositions. First, we'll put our discount inside our rebate. And then secondly, we'll do our rebate inside our discount. And let's figure out what this is going to be. Discount first, then rebate. So discount first, wherever we see our X inside our R, we're going to put the 0.92 right on in there. So 0.92 X minus 4,000. The second way of looking at it is rebate first, then discount. So if we do rebate first, then discount, then it's going to be wherever we see the X inside our discount, we're going to place this rebate value in there. So 0.92 times X minus 4,000. Go ahead and distribute this through, and you get 0.92X minus 3,680. Now the last part was, let's subtract these two values. If we subtract these two values, let's subtract D of R subtracted by R of D, and we get 0.92X minus 3680 minus 0.92X, which will ultimately be, we have minus 4,000, but when you distribute, that becomes plus. You get a total of $320. Now here's the thing. You get a better price of your car. Your car will cost $320 more if you do the rebate first and then the discount. It is better for you to do the discount first, then the rebate. Yes, discount first, then the rebate. It's better for you. It would cost you $320 more. And it doesn't matter what the car price is. It will always cost you $320 more if you apply the rebate first. than you do the discount. Discount first, then rebate. I mean, it's useful if you're going to go out and buy a car and they're doing a dealer discount and a rebate. Tell them you want the rebate second. Tell them, give me my discount first and then apply the rebate. They should do that. If they don't do that, I don't know if they're that honest with you. And you can do the math. You know how to do it now. So take a look at this problem. It is a real world problem here. If you are buying new cars, manufacturers do give rebates and dealerships do get discounts. Your better deal is to do discount first, then rebate. Discount, then rebate. All right, that's it for this lecture. Until next time, be seeing you.